Okay, just a very brief review here, a couple more things to say about bone fractures, and then I'm going to allow you to ask questions about your exam on Friday. Remember we said that bone is really made in two distinctly different ways. The first type was membranous ossification, which is really a phenomenon of flat bones. And really, below the skull, the only other set are the two scapulas that are made that way. So when I think about bone formation, I really think of this endochondral ossification. So most of the bones in your body are made this way from cartilage models. And we walked this through, remember, sort of giving some justification, some explanation for each step along the way. And we ended up with a long bone here at the end that has the epiphyseal plate or line has been sealed after the osteoblasts from the primary ossification center have really caught the chondrocytes. And so remember, this bone growth is occurring really in this epiphyseal plate where the dividing chondrocytes undergoing these massive mitotic rates in response to sex hormones and growth hormone and regulated in some ways by thyroid hormones, with all kinds of things necessary for this. The matrix then increases in this area, and the bone gets longer, and the sex hormones are also activating the osteoblasts from the primary ossification center, and these cells here are laying down bony matrix that's literally catching up with the chondrocytes in that epiphyseal plate. And eventually, normally along about the age of, on average, about 18 for a female, along about the age of 21 for a male, this finishes, and you end up with a bone like this, where you do have some hyaline cartilage on the ends. We call those articular cartilages. And then you have the cartilage now has been replaced with a bony line or plate there. And so it doesn't look like this anymore. Now, having mentioned the bone growth here, let's put this together at the end, the very end of this. Let's put these two concepts together and think about how bone is reshaped and remodeled throughout a person's lifetime. Remember when we started this with the bone anatomy, the big point that I was trying to drive home to you is that the bone, unlike its connective tissue cousin cartilage, is not vascularized. Sorry, so the cartilage, I said that wrong. Bone is highly vascularized, unlike its cousin, the cartilage. You look at cartilage and it's soft, you think, well, that's going to have some blood vessels in it, and it doesn't. You look at the bone, it's just this hard substance. You think, well, that's not going to have blood vessels in it, but it does. And so you guys now have a pathway in your minds where you can bring all of this rich blood supply into the bone and supply the osteocytes that are laying down the bony matrix. So you know that the osteocytes have the ability to do their jobs well. They're connected by gap junctions, and throughout the lamella, it's just the bone is really superfused with richness from the blood supply. So they can do their job well. In addition to that, we were talking about bone growth itself. You saw that these osteoblasts really like to lay down bone. And sometimes the student will get the impression toward the end of this presentation, toward the end of this, when I get to this last piece here, that, okay, well, once you've done this, it's done. You've made your bone, it's grown, and now you have a femur. And that's the end of the story. But that is not the end of the story. In fact, because of all the richness of supply for these osteocytes, they have the ability to reshape and remodel bones throughout a person's lifetime. So There is a phenomenon in your skeleton that is important to point out at the very end here. And it is a phenomenon called Wolff's Law. And here's what it says. A bone will grow and remodel in response to the forces or demands placed on it. Now, this is this is old information, but a relatively new strategy. This was in the past few decades, the way orthopedics handles bone fractures. When my youngest daughter was a baby, I broke the head of the radius on my left arm, being foolish. And I saw Dr. Garrison here in town. He immobilized it, put it in a sling and everything. And he did X-ray, and he saw there was a little 3mm fracture in the head of the radius. And then 3 weeks later, I went in to see him. And he took the sling off, and he said, Wade, this is going to hurt, but you've got some options here. You can either start moving this bone, or you can keep it still, and your recovery is going to take a long, long time. Now, when my dad was a teenager, he broke his arm. They put him in a cast that didn't let him move it for 6 months. What is the difference in those two? It really has to do with this Wolff's Law here, because we now know that if you can put some stress on a bone without causing further damage, that you can actually help that bone heal. You will activate the osteocytes in that bone to lay down more bone. And perhaps the easiest way to point this out by observation is these two observations here. Long bones, we know in the human body, tend to be thicker in the middle, where most of the stress is. And curved bones are thickest where they're the most likely to buckle. And trabeculae in the ends of the bones form along lines of stress on the bone. And maybe the easiest one for students to see in the laboratory is this one. There are large bony projections where heavy active muscles attach. So you might have wondered this to yourself. You should have. When the tibia is being made from cartilage, why does a knot appear on the anterior proximal side of that bone? Why does the bone in the lab have a tibial tuberosity? Why is there a deltoid tuberosity extending off of the humerus? Why, this one applied directly to me, why is there a knot on the head of the radius called the radial tuberosity? Why are there greater and lesser trochanters and greater and lesser tubercles? Pieces of the bone that are not smooth, they're sticking off of the bone. And the answer is, those are places where large muscles have attached and have, from the outset, every time movement occurs, the muscles are putting stress by pulling on the bone in that location. Another way of illustrating this would be to look at a professional athlete, and you'll start noticing these things now that you've had anatomy. You look at a professional athlete in the prime of their career, and they're huge physical specimens. And then you look at them 10 years after they retired. They don't look the same. Now, obviously, their muscle mass has been reduced, but it's more than that. Look carefully. Their bones are smaller. So as the muscle mass grows, the bones will grow with them, and the skeleton will actually get heavier and thicker, especially in support of those large muscles, which is the danger, I think some of you probably know this, is the danger in unnatural muscle growth. It's caused by injections of anabolic steroids. If the muscle outgrows in mass the bone that is supporting it by attachment, and the bone doesn't have time to grow with it, then what will happen? The bone will break. Yeah, the muscle will literally fracture the bone. And so this is a phenomenon in bone, and it can be explained in terms of what you learn about the blood supply for osteocytes. This is a living, dynamic, connected tissue in the body that reshapes and remodels throughout a person's lifetime. And we call this Wolff's Law. Now, there is one more interesting observation, and I'll mention this again when we get to physiology, so we won't do the details of it here. But there is another procedure that is used oftentimes with bone fractures to speed the healing process. So one way you can do this to get Wolff's Law to work in your favor is to pull on the bone. So that's what Dr. Garrison wanted me to do. He wanted me to contract my bicep. We talked about this. I said, what you want me to do is you know, Dr. Garrison, that the bicep is a two-headed muscle, but both heads attach to the radial tuberosity, right there on the head. The other two heads attach up here to the rim of the glenoid cavity, the coracoid process, and what you want me doing is you want me pulling on that radial tuberosity, don't you? He said, that's right. Because if you pull on it, what's going to happen? It has a way of activating the osteoblasts and osteocytes in the area to lay down bone faster. It speeds up the healing process. Okay, so Wolff's Law, reshaping and remodeling bones, and the bony projections that you learned in the lab, now you will think about them differently, I'm hoping. All right, let's talk about some fracture types and we'll be done with this. These are by definition, these are just to memorize for you. A comminuted fracture is one where the bone fragments into 3 or more pieces. This is particularly common in older individuals. You'll see this with the green stick fracture in just a second, that older people tend to have bones that are more brittle, and there's a reason for that. As we get older, the amount of living material, specifically protein material in the bone, reduces, and you end up with more calcium salts, percentage-wise, as you get older. It makes the bones more brittle, like the ones in the laboratory. A child's bone is flexible. Now, a young child, especially till the epiphyseal plates are sealed and the carpals and tarsals finish their ossification, a young child has rubber balls in them, right? They bounce off of everything. Yeah? The kid runs into something and they're 3 years old and they fall down, just don't look, right? Because if you look at them, they're going to cry. So don't look. Let them get up, because you know all that's hyaline cartilage, all those carpals in there, all those tarsals, they're going to bounce off of whatever they hit. But you take a person in their 50s and 60s and upward and they run into something, that doesn't look as pretty anymore. All that cartilage is gone, it's been replaced. So we get more brittle. These comminuted fractures are common in older people. Same thing here. Compression fractures are common in porous bones. So this is another topic that I'll bring up whenever we talk about osteoporosis and menopause in April. So why does this happen? What's going on with parathyroid hormone and sex hormones here? That's an interesting story. But for now, you're just learning compression fractions are common in these porous or osteoporotic bones. Elderly person falls or can even turn wrong sometimes and have a compression fracture in the vertebral column. This is a nasty looking one here, a spiral fracture. Spiral fractures are caused by twisting a bone, and this is a common sports injury. This one you recognize its name, don't you? Epiphyseal fractures. So where that line is formed, where the osteoblasts catch the chondrocytes during bone development, is a weak spot. Now, this is bad enough, but what would happen if a person 13 years old had an epiphyseal fracture? Is that different than an epiphyseal fracture in a 25-year-old?
You have growth plates.
Yeah, that's a serious matter, because now you can damage the chondrocytes. If you do that, you can end up with one leg or one arm longer than the other one. And so that's a very serious matter, these epiphyseal fractures.
Seems like nerve damage would be a major thing there.
Yeah, it's going to be very
bad.
painful. Yeah, all of the, as you are pointing out well there, all of the osteons have nerve supply, so certainly going to be a lot of pain. Okay, here's the last two. A depressed fracture is common in the skull. You can see the little depression fracture here. in the frontal bone. And then this is the one I mentioned just a second ago. These green stick fractures are common more in children where there's proportionally more organic matrix, so more collagenous material present in these bones. So they don't tend to snap, they tend to bend better. And so these bones have more collagenous, organic, proteinaceous material in them. Snapping is not a good word. They bend. They break in completely like a green twig breaks. Okay, this is where we begin test 2. I will teach you the sutures and the fontanelles about the fetal skull when we begin our test 2 material on Monday. So you have about 40 minutes. If that's not enough time, we can meet again before Friday. I wanted to leave this time for you to ask questions about exam 1. I will put at least 20 questions from last year's test online for you this evening, and you can use those as practice and sort of gauge how you're answering test questions. The test will have something in the neighborhood of 75 or 80 multiple choice questions on it. You will be able to choose 15 of those that you do not wish to have counted against you, and you will indicate that on the Scantron for me. I'll explain that just before you begin the exam. And those questions that you get right will count as bonus, like quiz bonus questions, if you get them right. If you get them wrong, they don't matter. So that'll relieve a little tension. You do not want to be late for the exam. Students like to read. You will have time to read the exam and answer the questions in about 30 to 35 minutes. So that's the way it's designed. Normally, a student or two will finish in the first 30 minutes. That normally scares me when a student does that. So if you're done in 30 minutes, just sit there and look at it for a few more minutes so that I don't get alarmed when you turn it in. But you'll be able to read it and answer it in about 30 to 35 minutes, which means you'll have an opportunity to go through the exam more than once. But think about your strategies before you arrive. You know there's 15 questions that you don't have to answer, that you can just put an answer for and move on. And so you want to, this is part of the learning process. Part of what anatomy does for you is it teaches you how to test. And so you need to think about how you're going to handle that before you get here. How you're going to mark that on your exam. You can write on your exam. So you're going to mark on the ones that you're going to look at a second time. Mark on the ones that you know for sure, the ones that you don't know for sure, however you want to do it. Just come with a plan in place when you get here. And you'll want to have, you'll want to come early. I'll get the test set up as quickly as soon as the class clears out, I'll set it up and you can come in and start. And you'll have the full time right up until 10:05. We'll keep you, because Dr. Criswell comes in at 10:10. So you can stay right up until that time. You could potentially have an hour and 5 minutes in here if you get here on time for the test. So there should be,
in this classroom. In this classroom.
There should be plenty of time for you to take the exam. But I will take it from you 5 minutes before Dr. Criswell has to start. So don't just read a question and spend 5 minutes on one question. That's why you have skips. Move on. Let that go. Answer the ones that you know and then come back to those. Now, your questions for me. Yes, sir.
Can you explain a little bit more the difference between the mesentery and the parietal peritoneum?
Yeah. So for me, Landon, if you say mesentery, you're really referring to parietal peritoneum. So I'm not going to make an issue out of that for you on your exam. I think it'd be more important for you to learn the parts of organs and the organs that sit outside of the parietal peritoneum. And then in a dissection how you would manage inside the body with that. So I compared, if you remember, the pockets for males and females at the most inferior regions where the parietal peritoneum forms these pockets. Those are very important locations, so you should know their names. And the same thing with the pleura, also, the recesses there around the lungs that are formed by parietal pleura. So parietal pleura then prevents you from getting through the diaphragm. Parietal peritoneum prevents you from getting into the pelvic body cavity. It also prevents you from getting to the kidneys and parts of the duodenum, and pancreas, and blood vessels. So, big picture there. I will not try to use mesentery in a way that would trip you up in your descriptions of peritoneum. To me, the mesocolon, and it is developmentally, that's a mesentery that hangs on to the descending colon, but it's actually parietal peritoneum. So, of all three of the serous membranes, this is the most difficult for me. It's hard to imagine, even when you do a dissection, it's hard to imagine where that stuff is. So, bottom line, mesentery is parietal peritoneum for me. But you will learn better one day on how to distinguish between those terms. And then you'll have to learn the names of them. They'll be called ligaments that attach various organs and stuff that will be part of the mesentery. All right, another question. Yes, sir.
You talked about it, but can you explain again why is the liver red?
Yeah, so for liver and spleen, and liver in particular, the tissue has a darker color. It looks red in a dissection, or almost like a dark purple almost. And the reason for that is the capillaries in those organs are anatomically different from capillaries in other organs. In the liver, we call them sinusoids, and they don't meet, which means all the hepatocytes and the extracellular spaces are superfused with red blood vessels. With red blood cells. So the tissue is literally permeated with blood. And that's where the color comes from. So that'd be very different. Let's say, for example, compare it to brain tissue. So you look at a brain, it's a nice light color. Does the brain not have blood supply? What's different about the blood supply to the brain?
Tight junctions.
The capillaries are all sealed up in the brain. Now, I wanted to make a point with that for you guys when we're talking about that in terms of colors everywhere. We're talking about gross anatomy. And so we have simple explanations for why things are the colors they are. And liver and spleen look that way because of the blood in those tissues. And you can explain that because you know about the junctions between the cells of the capillaries there. Sinusoids are a different anatomy than the capillaries in the brain.
So would that be like a gap junction?
No, gap junction's different. Gap junctions connect cells, cytoplasms, to the whole. So that would be something that would be true of cardiac muscle, right? And osteocytes, right?
What's the difference between desmosomes and gap junctions?
Desmosomes, yeah, and gap junctions. So a little simple picture will help. Cell 1, cell 2. solid desmosome. Cell 1, cell 2. Gap junction. Like the rivets on an aluminum boat. A hole, so two cytoplasms are continuous with each other.
For the cranial nerves, we need to know all 12 of them, but we only need to know the connections of the 4, right? Not the connections, but how they.
You know something more about the parasympathetic
Yes.
cranial nerves, right? The rest of them, you only know name and number at this point.
Just making sure.
Let me say a word about sequence questions. For example, if I wanted to do either a sensory or a motor sequence, and you have a sequence in your mind. So for sensory, you got the Ascidian corpuscle, dorsal root ganglia, dorsal horn, anterior funiculus, thalamus, cerebral cortex. For a motor pathway, you've got precentral gyrus, lateral funiculus, ventral horn, lower motor neuron, ventral portion, spinal cord, spinal nerve, muscle. So you heard me list like maybe 5 or 6 or 7 different things for each. So when I'm writing a question like this, so if we've got Ascidian corpuscle, dorsal root ganglia, dorsal horn, anterior funiculus, thalamus, cortex. The spinothalamic pathway, generally speaking. That's 1, 2, 3, 4, 5, 6. 1, 2, 3, 6 different items there. When I'm writing the question will say which of these is the correct sequence for a dorsal pathway. I'm not going to put all 6 of them. So I'll choose, I have this list in my head. So I'm going 1, so this is 1, 2, 3, 4, 5, 6. But I'll say on A, I'll have 1, then 4, then 3. Choice B will be 2, then 5, then 6. That's the right answer. Choice C will be 3, then 5, then 2. But by asking the question that way, my student must know the entire sequence to get it right. So just because it doesn't follow exactly, the next one doesn't follow exactly in line, it doesn't mean it's the wrong answer. I'm looking for the correct sequence, and I may skip some of the steps. Do y'all understand that? So that would go for sensory or motor pathways. I can do it that way. And there are other sequence things. None of them come to mind at the moment, but there will be others. Every test has it on it. So just read those carefully. When you see the right one, you say, that could go there, could go there. Just mark that and don't read the rest of them. Or another way to approach this, I see students doing this all the time. If the question says, track the sensory pathway, just write it out. Don't look at the answers. Just write it out. Because that's the way the question was made. And then look at the answer and go, yep, 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 yep. So like on the next test, you're going to do that with the brachial plexus, because I'm going to ask you probably 10 or 15 questions from it. And if you try to go back through the plexus every time, you're going to waste enormous amounts of time. So when the test starts, you just draw the plexus out. And every time you get to one of those questions, you just look over there and you go, yep, that's it. So you don't waste a lot of time that way. I see, as he's just going through tissue slides here, a couple ways to do these. A lot of times what I'll do is I'll have, the question will say, which of the following correctly couples tissue with location? That way I can take you to 4 different places in one question. And I'll just list the tissue / location. Tissue / location. I'll do that. The other thing I'll do sometimes with these, yeah, the other thing that I'll do sometimes with these questions is I'll, like, as we went through the different tissues, you actually learned anatomy of some of the systems in the body. And I try to point this out while we're doing it in class. For example, you haven't learned the respiratory system yet, have you? Or let's say, have you? For example, if I went in the respiratory system in my nose, what would be lying in it?
Simple. No.
Stratified squamous, okay? As I got into the pharynx, what would I find? Right deeper, but before I get to the columnar, ciliated, pseudostratified columnar with goblet cells. Then I would find ciliated or non-ciliated? Ciliated columnar. And then when I get to the bottom in the alveoli, what would I be in? Simple squamous. See, you learned that over the course of several slides. I'm going to put that together on one question. How about the digestive system?